We will do only one section in chapter 13. Chapter 13 is primarily on chi-squared testing, and I don't really have time to go into any more of that, but it's a valuable tool. You hear a lot about chi-square testing, and if nothing more, I would just love to give you an example of chi-square testing, so when you hear about it, you can say, hey, I actually did that in stat class. It's kind of a cool thing, what you can do, okay? So let's talk about it. Where can you use chi-square testing? Are two species often found together, different kinds of plants? Do they often grow up together? You could use chi-square testing to establish that. Whoa, is there a gender gap in your chances of dying in a slasher movie? Do women get killed more often in a slasher movie than men? Probably so. Are we getting the correct proportion of colors in a bag of M&Ms? Kind of an interesting thing. Now, some different things about chi-square tests. I want to give you all of this, but basically I'm just interested in, can you do a problem, okay? And you'll be able to see how cool chi-square testing really is. What we did, when we did hypothesis testing in chapter 9, we wanted to determine if the mean had changed. Was it either smaller, left-tailed test? Was it larger, right-tailed test? Or was it different, a two-tailed test? You don't have to worry about any of that in chi-square. You are just simply looking to see if it's in the reject or not reject. That's all, okay? Much, much easier. To do a hypothesis test, and when we're adding two or more normal sets of squared data, we use chi-square distribution. In chi-square, it's very helpful to see if sigma has changed. Has the standard deviation changed? Whereas the hypothesis testing we did in chapter 9 was to see if the mean had changed. All right, a chi-square curve is right skewed. You should remember right skewed. Right skewed looks like that, okay? The curve starts at 0, which is odd. We are used to having curves that start out on the negative side and go to the positive side, right? Okay, so negative and then going to positive, and it's right skewed. Area under the curve is always 1. Curve starts at 0. It'll always be right skewed. As n increases the degrees of freedom, you remember degrees of freedom from t-tests. As they increase, the curve becomes more and more normal. I'll show you a picture of that in a second. All expected frequencies are 1 or greater. At most, 20% of the expected frequencies are less than 5, simple random sampling. These are the assumptions for chi-square testing. As I said, we're going to keep it ultra simple. I just want you to be able to set up a problem and do the problem to have some kind of experience with chi-square problems. Okay? So, here's a picture. As n gets larger, as it goes from yellow to red, you can see everything is right skewed. But as you get down here to the purple and the reds, it's looking like it's getting more and more normal, okay? Which it is, all right? Notice as n increases, the degrees of freedom also increases. The curve gets more and more normal, all right? One thing also to remember that the degrees of freedom is always 1 less than the total number that you're working with, okay? We ran into that with t-testing. All right. Some other things, chi-square values are in table 7 on pages A14 and A15 in the back of the book. Here is your symbol for chi. It kind of looks like a letter X. And the table will always give you the area to the right. So this you should be familiar with when we were working with z-charts. Find the chi-square value that has an area of 0.025 to the right and 12 degrees of freedom. So you got to go in the back of the book. Let's go to the back of the book. And in the back of the book, on page A14 and A15, we want to find the chi-square value that has an area of 0.025 to the right. Now, if you look at your headings at the top, you have to go over to page A15. You got to go over to page A15 to find 0.025, okay, and 12 degrees of freedom. You go down to the 12, and you should get 23.337. Everybody with me? Okay? Find a chi-square value that has an area of 0.05 to the left with 7 degrees of freedom. If it has an area of 0.05 to the left, okay, to the left, right, it's going to have 0.95 to the right. Yeah? So you want to find chi-squared of 0.95. It's on page A14. Find 0.95. And we want 7 degrees of freedom. So we've already subtracted the 1. Go down to 7, and it should be 2.167. Okay? You will never do this, but I just wanted to refresh your memory. Okay? Suppose n is 20. Find the two chi-squared values that divide the area into a middle region of 0.95 and outside areas of 0.025. Remember doing these for two-tailed tests in chapter 9? Middle region of 0.95, if the outside area is 0.025, you know you're going, let me draw it, you know you're going to have something right skewed. We want the middle region to be 0.95. So this area right here is 0.025. This area over here is 0.025. But you got to be careful because your chart gives you areas to the right. So how can I find the chi-squared value for this first one right here? Okay, how can I find that? It's got to be this area to the right. I have to add those up. Is it not 0.975 to the right? Okay, so go on your chart on page 14, find the heading 0.975. N is equal to 20. We got to take 1 off. We're going to go down to 19. And you should have this one is 8.907. Yeah? And then this one is an easy one. The area is just 0.025 to the right. Okay, so you go to 0.025 and go down to 19 is 32.852. Okay, and as I mentioned, you will not do any like that. I just wanted to remind you, a helpful reminder of chapter 9. Okay, now how about hypothesis testing with chi-square? All right, Sam is thinking about buying a computer store, okay? The current owner is trying to encourage her to purchase the store by telling her that the customers usually average 12% come in on Tuesdays, 17% on Wednesdays, 15, so on, so on, so on. Sam doesn't trust the owner. She parks outside the store for a week and observes the following, okay? It does look like most of the customers come in on Saturday and Friday, but do they hold true to those percentages? Okay, we're going to test this at the 5% significance level. H naught is the initial hypothesis that the expected values are statistically true at 5% significance level. Okay, the alternative hypothesis, just like chapter 9, the values are not true. Okay, so we're going to test it. Find the expected values. Now, you got to make a chart. So here we have the expected values, the observed values, okay? Then you have a column, O minus E, quantity squared divided by E. I think that's the only one you need, okay? Then you're going to add this up down here, right? And we're going to compare it to the critical value at the 5% significance level. So draw a picture. Starts at 0, right skewed. Now, we want 5% significance level. So get your chart. We want 5% off to the right. Okay, so we want an area of 0.05. You're going to have to go over to page A15. Okay, how many data items are there? Tuesday, Wednesday, Thursday, Friday, Saturday. Isn't that 5? Tuesday, Wednesday, Thursday, Friday, Saturday. Yeah, there's 5 of them. Okay, nothing on Sunday and Monday. So you got to take 1 off. So you're going to go down to 4 when you're at 0.05, and it should be 9.488. Okay? I think if my brain is working. Okay, so just going to double check that before we go any further. And if I can find it, yep, 9.488 is perfect. All right, so let's get back to where we were here. So our critical value is out here at 9.488. So here's 9.488. And we want to see, here is the do not reject, and here's the reject. So we just want to see where it falls. Okay, so let's do the work. All right, so the expected values. Well, how many customers showed up when Sam was observing? Let's say those up. We have 25 and 32 is 57 plus 36 plus 75 plus 90 equals, I get 258 customers, okay? So there's 258 total. If what the owner is saying is true, 12% of them should be in on Tuesday. So I'm going to take 258 times 0.12. That should be 31. Okay? I'm going to take 258 times 0.17. That should be 44, rounding off the whole number of people. I'm going to take 258 times 0.15. That should be 39, rounding off the whole number of people. Okay? I'm going to take 258 times 0.26. I get 67, and 258 times 0.3, and I get 77. There's the expected people that Sam was looking for. Okay? Now, what was observed? Okay? What was observed were 25, 32, 36, 75, and 90. Now, by the way, don't get all messed up about trying to memorize that. I will give you the column headings on a test, okay? All you've got to do is be able to understand how to set up the chart and then work it out. All right, so now I've got to do O minus E divided by and square it and then divide by E. All right, so you do the squaring on the top first. And because it's squaring, I don't care whether you subtract E minus O or O minus E. It doesn't matter. Negatives are going to square and become positive anyway. All right, so this is a difference of 6 squared is 36. 36 divided by 31. Everybody get what I did? Is 1.16. Difference here, 44 and 32 is 12. Squared is 144 divided by 44 equals 3.27. 39 minus 36 is 3. Squared is 9 divided by 39. I get 0.23. 67 to 75 is 8. Squared is 64 divided by 67. 0.96. 77 to 90 is 13. Squared is 169 divided by 77 equals 2.19. Add those babies up. And I get 7.81, and look where 7.81 is. It is in the do not reject region. We can agree that the owner's expected values are statistically true. Is that neat or what? Okay, fantastic. Well, let's do another one. I think this one is in the textbook. Okay, first we're going to test to see if crimes have changed from 2000 to 2017, okay? Back in 2000, the most number was assault, and if you look in 2017, the most is still assaults, okay? The smallest number was murder. 1.1% was murder, and the smallest number is murders. okay? But have they statistically changed from 5%? So we're going to do the same thing. Set up a right skewed. We want 5%. So you've got to go to your table. And we're going to do, we want 5% out here. This is 0.05. And we have how many categories? Crime. Aren't there 4 of them? 1, 2, 3, 4, yeah. So you want to go to 0.05, which means you have to go to page A15, and you go down to 3, which is 7.815. Check that. So this is the critical value, 7.815. All right, now we're going to do the same thing, chart. Okay, we have expected, observed, expected minus, I think it's the other way around. O minus E, pardon me. Doesn't matter, same thing, divided by E. Okay, and then we add up this. All right, so let's do it. First, what would be expected in 2017? Well, let's add up the total number of crimes. So we have 3 plus 37 plus 154 plus 306 equals 500. Nice, easy number. So we have a total of 500 crimes. Okay? 1.1%. So take 500 times 0.011. I get 5.5. Okay, how about for rape? Take 500 times 0.063. How about everybody seeing that okay? Looks good. How about robbery? 500 times 0.286. Lots of those. And the most would be assault. So we want to take 500 times 0.64. I think that's 320. Is 328. Now, what was observed? What was observed? We had 3 murders. We had 37 rapes. We had 154 robberies. And we had 306 assaults. Subtract, square it, and divide by the expected. Okay, so when you subtract here, you get 2.5. Squared is 6.25 divided by 5.5. 6.25 divided by 5.5, I get 1.14. 37 minus 31.5 is 5.5, so square that. And then divide by 31.5. And I get 0.96. 154 minus 143 is 11. Squared is 121 divided by 143. I get 0.85. 320 minus 306 is 14. Squared is 196 divided by 320. And I get 0.61. Add them up. I get 3.56. 3.56, whoa, way down there. Well within the do not reject. H naught. H naught was that crimes have stayed statistically the same since 2000. Okay? The alternative hypothesis is that they're different. They've changed, and they did not. It's in the do not reject region. You should be able to make a concluding statement like that. Okay? Is this great stuff? This is the only thing we will do. Whoops. The only thing we will do in chapter 13 is to do chi-squared. We'll wrap up this course by going on to chapter 14 our next time together. Oh, homework, heaven's sakes. Heaven's sakes, there's your homework. Okay. A couple of extra problems then below the chi-squared problems.